Hello everybody, today I'm going to talk about how to use Taylor series expansions to predict a function value. Here I give you guys a very specific example using the function fx equals 25x cubed subtract 6x squared plus 7x subtract 88. And we wanted to predict the function value at x equals 4.5 using a base point at x equals 1. First of all, we would like to recall what is Taylor series. As we know before, a Taylor series can be written as like this guy. Here, xi plus 1 is the predicted value, xi is the base point, and rn is the residue, can be written as this guy. Okay? Now, if we let h equals xi plus 1 subtract xi, we submit this guy to above Taylor expression, then we can get this guy. Okay, so basically we just replace xi plus 1 subtract xi by h, and where rn equals this guy. Okay, so that is our Taylor series expansion. Now, for this example, we have what? As I mentioned before, the base point xi equals 1, and the prediction point is 4.5, and the h is the difference of these two. 4.5 subtract 1 equals 3.5. And also, as we can see in the Taylor series expansion, we have the derivative, right? We have the derivative. Here we're gonna calculate the first, second, and third derivative. So giving the fx in the above example, we calculate the first derivative as 75x squared subtract 12x plus 7. Okay, and then we do the derivative again for this function. We're gonna get the second derivative of this function, and if we do the derivative again, we're gonna get third derivative of this function equals 150. Okay, now let's substitute these three variables into above Taylor series expansion. We're gonna get here xi plus 1 is 4.5, xi is 1, and h is 3.5, and we got this very specific Taylor series expansion for this example. And this guy gonna be our approximation value. Okay, approximation value using the Taylor expansion. Now, how to evaluate the true value f 4.5? The true value is gonna be plug in 4.5 here. Okay, that is the true value. The true value is gonna be f 4.5 equals 25, which is plugging in for the function, and we're gonna get this value. Okay, that's the true value, and this one is very important. Okay, now let's go to the zero order Taylor series expansion. Okay, for the zero order, we're gonna go back. We're gonna keep this term and remove all the other terms. Then we call this guy as zero order. Okay, we only keep f1. If we only keep f1, we just plug in the f1 value, we plug in the function, we're gonna get plug in the function, we're gonna get -62. Okay, and now we can evaluate the relative error. The relative error can be written as true value subtract approximation divided by true value. As we know, the true value is 2100.13. Right? Subtract the approximation is -62 divided by the true value, gonna be 103.1. Now we wanted to calculate the first order. First order, that means we wanted to keep the first two terms. Okay, so let's take a look. The first two terms gonna be this guy. Now we're gonna plug in, evaluate f1 and the f1 derivative, right? We already know the fx, the first derivative of fx. So we're gonna plug in, we're gonna get 183. Again, we're gonna calculate the relative error. We plug in the true value, it's still this guy, 2100.13, subtract the approximation value is 183. Divided by the true value, and we obtain 91.29%. Okay, how to evaluate the approximation relative error? The formula is here. Current approximation subtract the previous approximation divided by current approximation. As we know, the current approximation is 183. The previous approximation is -62. Just plug in, we're gonna get 133.9%. Okay, for the second order, we're gonna keep three terms, right? 1, 2, 3 terms. Okay, so then we plug in. We calculate f1 is -62, f1 prime is 70. And the second derivative of this guy, then we're gonna get this one and plug in it, and we're gonna get the result 1028.25. Then we can evaluate the relative error and plug in and subtract this approximation value here, and we're gonna get 51.04%. And the approximation relative error gonna be this guy. We have the current approximation is 1028.25, subtract the previous approximation is 183, right? And we're gonna get 82.2%. And the third order, again, we're gonna keep 1, 2, 3, 4, 4 terms. 1, 2, 3, 4, 4 times, and plug in all the values, and we're gonna get the value is 2100.13. And again, plug in the formula, we're gonna get relative error, and also we can get approximation relative error. We plug in the current approximation, subtract the previous one, divided by the current. And the final result is going to be 51.04%. That's it.